Hello everyone, this session is for students transitioning to A-level chemistry, and the topic is isotopes and relative atomic mass, something which you will have encountered, certainly the names of these two things, isotopes and relative atomic mass, at GCSE, but we're going to go into a little bit more detail to make sure you have a firm knowledge for going into the A-level content. So this session we'll look at knowing parts of element symbols and definitions of isotopes and RAM, which is relative atomic mass, and also identifying isotopes and calculating relative atomic mass. As for the AQA specification. So a little bit of a starter for you. We're going to first see what you can remember. So have a little look at the tasks on the screen. If you'd like to pause the video now, then you can have a go at some of these tasks. The next slide that I'll go to will go through the answers for those, and again, if you have any issues with these, please post onto MS Teams. Okay, so if you didn't pause or you're not sure, I'm going to go on to the next slide now. So if you haven't quite finished the task, pause again here and I'll go on to the next slide with the answers. That would be the periodic table, and then of course the answers here. So you will have used the knowledge you have of element symbols to deduce that the atomic number was 11 for sodium. The mass number is 23, and that means that the proton number is 11, as it's always the same as the atomic number, and the number of neutrons is 12, and we get this from the subtraction of the number of protons, 11, from the number of total relative mass, which is 23, and that gives us 12, and then as it's an atom, it has no charge, it's neutral, which means that the protons and the electrons are equivalent, so therefore with 11 protons we must have 11 electrons. Again, the protons having positive charge, 11 of those positive charges, and 11 of the negative charges for electrons in the atom sodium. That's the atom sodium. Okay, so you could have worked out the rest just by being given this basic information. And so you should have been able to fill in the rest of that data, even if you weren't given the element symbols. You could have gone to the periodic table on the previous slide here to go and check those if you want. That wouldn't really have been in the spirit of things, but certainly it means that you should have been able to predict those. On to the next part here. Well, this is leading into our first topic really, which is isotopes. There are no half protons and half neutrons, of course. Well, I mean, don't ask a physicist, but yes, as far as chemists are concerned, we don't do anything smaller than an electron, certainly at A level anyway, unless we're talking about the wavelength of light, which we'll cover a bit later in colorimetry. So, essentially, the reason that we don't have a whole number is because there are isotopes, and this will lead us into our session. So a quick reminder of what we're going to cover today. And then now into isotopes. Well, generally when we work out what the different isotopes are, then we need to take a sample and we need to smash it up, and this means it can then go through a mass spectrometer, and we get a mass spectrum, which is representing the abundances of the different isotopes. So you should know what an isotope is, but essentially an isotope is an atom of the same element which has the same number of protons, therefore, because it's the same atomic number, same element, but different numbers of neutrons. The example I've given here is for copper. So you'll see that when you smash up naturally occurring copper, you find two major isotopes, two different variations of an atom of copper. Copper with a mass of 63 and copper with a mass of 65. So I have this represented over here and exactly what that means. Again, notice the electrons are the same because the protons are also the same, and we can also therefore say that they are the same element because the protons are the same. Now, the only thing that's different is the number of neutrons, and that's the neutrons in the nucleus there. Now, what I'd like you to do then, see if you can work on a definition of isotopes, and then also for a different example here, work out what the protons, neutrons, and electron numbers are for these two isotopes, in this case, of chlorine. So again, pause the video now and you can have a go at writing those down. The answers will be on the next slide. Okay, so I'm going to go on to the next slide now. So this is what you should have been able to deduce in terms of filling out the grid, but also here's the missing words there, so you get that definition of an isotope correct. We'll return to the mass spec here in a second, and we'll just go on to the next bit, which is looking at relative atomic mass. So, from right at the beginning of the lesson, we would have seen that the mass number of copper is a relative atomic mass. So that's the symbol A with a lowercase r there, or subscript r. And this is because not all the atoms of copper are the same. Most atoms have a mass of 63 and some have a mass of 65. Well, so we know that copper 65 and copper 63 are isotopes of copper. So why is it then that the copper, the atomic mass of copper, the AR that is not halfway between at 64? Why is it also a decimal, 63.5? So we need to then look at the fact that there are naturally occurring isotopes. So naturally occurring, there are copper 63, or there is copper 63 atoms, and there are copper 65 atoms. There are barely any copper 64 atoms in existence at any given time, so we don't factor them in, but there are actually 26 other isotopes, or radioisotopes, we're not taking into consideration, mostly because they're only in existence for something in the realm of nanoseconds, so don't worry about those. Essentially, if it's not very easy to detect on a mass spectrometer, then it doesn't tend to be factored into calculations, and certainly not at A level. Okay, so here's that mass spectrometer again, and it also confirms then that majority of the copper atoms are copper with a mass of 63, and that's 69%, and then copper 65 is only 31%. So if we were to take any given lump of naturally occurring copper, 69% of it would be copper 63, and 31% would be copper 65. How then do you calculate based on this knowledge of their abundances? We need to do a calculation which is slightly more sophisticated than a simple average. And we use this formula. So here's the formula here. It's the sum of the mass of isotope 1 times its abundance, and include also the mass of isotope 2 plus its percentage abundance. Now, if there are more isotopes, for example 3 or 4, you just simply add more isotopes onto this area here above our division line, and then divide that by the total abundance. Now, if you're doing percentage abundance, then of course the total abundance will always be 100%. So as far as we're concerned today, everything will be divided by 100, as our percentage abundances are being used. It's not any other measure of abundance. Okay, so let's have a little look at an example of how we would do this. We're going to have a look at sulfur, which has 2 isotopes, more likely 4, but again, for our purposes, we'll say it has 2 major ones. Let's have a look then. We've got sulfur 32, so that's a mass of 32 for that isotope, and there are 96% of atoms in naturally occurring sulfur are sulfur 32, and then we have sulfur 34. Only 4% of naturally occurring sulfur atoms are sulfur 34. So what we then do is we use our formula, which is just above here, and we apply. Oh yes, I must say that as well. It's a good job I put that in there. What I'd like you to do is also develop kind of a chemical sense and a number sense. So actually, if we think about it, it's got to be somewhere on the line between 32 and 34. So I know you may not have used lines, as it were, in maths for quite some time now, but do you think that it's going to be closer to 34 or 32? Well, I mean, you could say it's going to be 96% towards sulfur 32 and only 4% towards sulfur 34. So that would mean it would most likely be closer to sulfur 32. Of course, it would never ever be sulfur. It would never ever be 34 because, of course, with sulfur 32 there, even if it was a minute amount, it would always mean they would never reach that as an average because everything would be lower than 34. So, just thinking about it before we actually calculate, probably quite close to 32, 96% towards sulfur 32. Let's now apply that into the formula. So we then have the sulfur 32 mass of that isotope times its abundance, 96%, plus the mass of the isotope sulfur 34 times the percentage abundance, which is 4%, and then divide that by the total abundance. In this case, 96 plus 4 is 100, and that gives us then a percentage abundance of 100. So, just as good practice, it's very good to solve things. Now, if you feel like doing this in your head, you can. If you must use a calculator, try and use one. And if you haven't got one, by the way, get yourself a nice graphic calculator. Bring it to every single lesson. And also make sure you have a backup. This would be an investment for 2 years of your chemistry A-level. And you will take it into all exams. And don't lend it to anyone, not even if they ask nicely. That's your calculator. Put your name in it, put a sticker, some kind of permanent marker, make sure no one ever gets to touch that. So let's solve it. First we're going to get rid of those brackets and then we're going to add things together and then it becomes a nice simple sum. Then we end up with a relative atomic mass of sulfur of 32.08. So that means yes, it is closer towards 32, 96% closer towards 32 than it was towards sulfur 34. So that's how that one was calculated. Not too difficult, but you just need to make sure that this is something you can do readily and easily. Okay, so here's an opportunity for you guys to have a go. So I'm going to go very quickly on this one because I'd like to pause the video and have a go at that one. Again, add on additional isotopes and their percentage abundances above the line there, and then you'll be able to work out what it was. I've given you some options here, but you can probably do what I suggested you do, and again, think, is it going to be closer to 28, 29 or 30? So you can probably make a guess and then actually do the full and fine calculation. So I will tell you now to pause the video. Okay, right, so you should have paused the video and had a go at those. If you haven't, then make sure you do that. I'm going to go on to the next slide now. So it is indeed 28.11, and if we have a look, this was the sum that you should have done, and then you would have got rid of those brackets, made it nice and simple, and then you would have got to 28.11. Okay, so I have some challenges for you. Have a look at these. I'd like to post your working out on the MS Teams chat, and then we can discuss those a little bit further. First one's nice and easy, second one much harder in comparison, but you should be able to do it. You will need to use extensive math skills. As a little hint for you, it's a little bit of algebra. Okay, so again, pause the video now and you can have a crack at those. Take a screenshot, do whatever you like, and then post your working out onto the Teams chat. myself and Mr. Mohammed, Mr. Bassi would very much like to see how you get on with these challenges. Okay, so one final slide to show you. This is that by now we've gone through the parts of the element symbols, the definitions of isotopes and relative atomic mass, and then also being able to identify isotopes and being able to calculate relative atomic mass. Further resources you might need, Seneca, Mr. Mohammed will share details of this. Also referring to the AQA textbook, you should have been set up on Caboodle for that. And we also have access to the Head Start to Chemistry Kindle book. I think it's on page 3 or 4 of that one. So you can download that and use. You can actually view that on your PC as well. You don't need to have that on a phone or a tablet. You can actually use that on your PC, and it might be quite good to use alongside this. Alright, thanks very much for listening. Any other questions, post it in the MS Teams chat.